Section 5.2 Area. By the end of this section, you should be able to use sigma notation and to write and evaluate a sum. Describe the concept of area, approximate the area of a plane region, find the area of a plane region using limits. Sigma notation.
So this symbol here, it's called sigma notation, and this is the starting value k equal 1 up to k equal n. This is AK. AK is the formula for the kth term. For example, let me just give you one example. Uh, if I say k starts from 1 to 5 of, let's say, AK, the meaning of this is there are 5 terms: A1, A2, A3, A4, and A5. I'm just replacing this k by from 1 to 5. And then in between those terms, there is a symbol plus. Sigma notation means summation, sum of all these terms starting from 1 to 5. Okay, so some of the examples here, as you can see, the first one, k equal 1 to 5. In our case here, AK is k itself, so we are just plugging k equal 1, 2, 3, 4, 5 and adding them. The sum should be 15. Second example here, k equal 1, 2, 3, so there should be 3 terms, and then each term has negative 1 to the power k. Wherever you see k, you just replace that by 1, 2 and 3, and then if you add them, you are going to get negative 2. That's the sum. And if you do the same thing for third one and fourth one, wherever you see k, you just replace that k by 1 and 2 for the number 3, and that will give you this sum 7 over 6. For number 4, you replace k by 4 and 5. It starts at 4 and it goes up to 5. So k equal 4, k equal 5, and that's the sum. So these are the some algebra rules for finite sum. So sigma notation of AK plus BK is actually sigma notation of AK plus sigma notation of BK. So you can split that, and there is a minus sign, so you can split that. And if you see, some constant times AK, then you can bring that constant outside. And constant value rule means if you are trying to find out the summation of C from k equal 1 to n, there is no k in C. C is constant. So what you are doing here is, when k is 1, the value of the term is C. When k is 2, the value of the term is C again. And you go up to, n many C. That's why the value would be n times C. These are some rules. And there are some formula for standard summation thing. For example, if you would like to add first k n natural number, that is n times n plus 1 over 2. This is actually 1 plus 2 plus up to n. So this is the sum of the first n natural number. This is sum of first square of the natural number, first n natural number. This is sum of cube of first n natural number, and that's the formula. Whenever you have this kind of sum you would like to find, you can always use this formula. One example here, express the following sum in sigma notation. So as you can see here, start from 1 and it goes up to 25. There is nothing is missing, 1 2 3. So the first term is 1, second term is 2, third term is 3. So we can say that kth term is k itself. Okay, if we just replace this k by 1 for the first term, 2 for the second term, 3 for the third term, and we're just adding all those terms. That's why we have to introduce this sigma notation, and that k is going from 1 to 25. This is the sigma expression for this sum. If you want to find out the value of this, you can use this formula, n times n plus 1 over 2. Here in this case n is 25, so 25 times 25 plus 1 over 2, which is 25 times 13, which is what is that, 250 plus 75 is 325. I'm just multiplying 25 times 10 plus 25 times 3.
Area. In Euclidean geometry, the simplest type of plane region is a rectangle, meaning if you have given a rectangle, it's very easy to find the area of the rectangle by using this formula, area equal b times h. Um, it is more proper to say that this is the definition of the area of the rectangle. B, it's a width time. Let's say you have a rectangle like this. Let's say one side of the rectangle is B, another side of the rectangle is H. If you multiply these two sides, it gives you area. We have area for the triangle, like area of a triangle is half times base times height. We have area for the parallelogram, hexagon, polygon. We can find the area for this regular geometry. Finding the area of the region other than polygon is more difficult. If you have a polygon like this, it's very easy because you can divide them into different triangles. The ancient Greeks were able to determine formula for the area of some general regions, principally those bounded by conics, by the exhaustion method. The clearest description of this method was given by Archimedes. Essentially, the method is a limiting process in which the area is squeezed between the two polygons, one inscribed in the region and one circumscribed about the region. For example, in the figure, the area of the circular region is approximated by an n-sided inscribed polygon. For each value of n, the area of the inscribed polygon is less than the area of the circle, and the area of a circumscribed polygon is greater than the area of the circle. As n increases, the area of the both polygon become better and better approximation of the area of the circle. A process that is similar to that used by Archimedes to determine the area of the plane region is used in this example. So by using the very same idea, we're going to find the area under the curve in this section.
Let's assume that we would like to find out the area under this curve, which is R, region R. So we would like to find out this area. So if we had something, a regular figure like triangle, then there is a formula for finding the area of the triangle by using half times base times height. Or let's say we have a structure like this, which is a rectangle. Then there is a formula, length time width. Okay, so there are the formula for finding the regular structure like this. The area for the first one is half times base times height. The area for the second is length time width. Sometime, we can also find out the area of let's say sometime we might have a structure like this, which is a square. Area of the square is just square of the side of the length of one side. So we know how to find the area of this kind of regular structure, but we don't have any formula for finding the area of this kind of region, this kind of region. So what we do, we try to use area of the rectangle to approximate the area under the curve like this, which gives us not regular region. So let's say here the first part, there are two parts I'm using. If we divide this region into two equal parts from 0 to 1, I'm dividing that into two different pieces. From 0 to half is 1, and from half to 1 is another one, by dividing them into two different rectangles. So as you can see here, we get an upper estimate of the area of R by using two rectangles containing R. So as you can see that we can find out the area of the first rectangle, which is height. Height is 1 because the value of the function at 0 is 1. So this is the height times width. So this is the height, which is 1, and then width is half. So area of the first rectangle is half. Area of the second rectangle is half times 3 over 4, which is 3 over 8. So sum of these two area of the rectangle would be greater than the area of the region R. And instead of using two rectangles, if we use 1, 2, 3, 4 different rectangles, then again the sum of this area of this rectangle would be greater than the area of the region R, but now it would be more closer to the area of the actual region compared to, by using two rectangles. So what I'm trying to say is, if you use more rectangles, then your approximation, your area of that those some of those rectangles would be more closer to actual area of the region. So here, to draw this rectangle, we are using the right endpoint, right? We're using the right endpoint. No, we're using the left endpoint. So from here, if we draw a rectangle from this point, so we are using the left endpoint. Again, we're using the left endpoint. For the very same rectangle, we can also use uh, the left endpoint. So meaning I can divide from 0 to 1 into 1, 2, 3, 4 equal pieces. And I can use the right endpoint to construct these rectangles. These rectangles, the sum of this area of the rectangle would be less than actual area. But if I divide this region from 0 to 1 into more pieces, then I will have more rectangles, and then my approximation would be more closer to the actual area. So this is the picture A. Rectangles contained in region R give an estimate for the area that undershoot the true value by the amount shaded in the light blue. And then here in this case, we are trying to create a rectangle using the midpoint of each of this subinterval. So what is happening here is we are dividing from 0 to 1 into 1, 2, 3, 4 equal pieces. And then from each piece, we are trying to construct a rectangle using the midpoints. Here, we are, dividing again into 1, 2, 3, 4 equal pieces. But to construct this rectangle, we are using right endpoints. You see that? If you go to the previous picture here, again here, 1, 2, 3, 4 equal pieces. But to draw this 4 rectangle, we are using left endpoint. Whereas here in this case, we are using the right endpoints. So depending on what you use, either you use the left endpoint or the right endpoint, sometime you might get less area, sometime you might get more area. But if you draw this number of rectangle more and more, your approximation of the area would be closer to the actual area. So let's go to the another slide here. As you can see, if I draw more rectangles, either by using the rectangle, by using the left endpoint or the right endpoint, if I draw more rectangles, the area of these some of the rectangles would be more close to the area of the region we are looking for. Okay, so in this case, part A on part B, we are using 16 equal pieces, meaning we are trying to divide from 0 to 1 by 16. So we're trying to create 16 rectangles. And when we try to do that, for this picture, we're using the left endpoint to draw these rectangles. And here we're using the right endpoints to draw the rectangles. Okay. So now, based on our information, based on the number of subinterval, whatever we use, we get lower sum, mid sum, and upper sum, depending on how we are creating that that rectangle. So let me go back one more time. In this picture, as you can see that here we are using upper sum. Upper sum means rectangles, some of the area of the rectangles are bigger than actual area. In this case, we are using the lower sum because some of the rectangles are smaller than the actual region. Here we're using the midpoint, so that's called mid sum or midpoint sum. So based on that, how we draw that rectangles, we get lower sum, midpoint sum, and upper sum. So if for the very same problem, if we use two rectangles, number of sub-interval. If we use two sub-interval, then lower sum would be 0.375 because it would be less than actual area. If we use the midpoint of those two intervals to draw the rectangles, then midpoint sum would be 0.6875, whereas the upper sum would be 0.875. And you can always get this area by multiplying width times height. So just to check, this is the upper sum, right? So to find out the area for the first rectangle, that would be height, which is 1, times the width, which is half. So this is half, and here width is half, height is 3/4, so it would be 3/4 times half, which is basically 3/8. So the sum would be half plus 3/8. So which is basically, this is if you use your calculator, so half is 0.5, and then 3/8 is, I'm using my calculator here, 3/8 is 0.375, so it's a 0.5 and it's a 0.375. If I add these two number, then it's going to give me 0.875 by using the upper sum. That is what we are using here. Look at here, the upper sum for the two sub-intervals. The upper sum would be 0.875. So we are talking about area of these two rectangles. Okay, and here if we do this very same thing, and if we try to draw the two, if we try to divide this interval, this whole thing into two interval by using the lower sum, the lower sum would be 0.375. If we use the midpoint, this would be the area of the rectangle. So more we go further, meaning more we use sub intervals, there will be more rectangles, and more further and further, as if you just look at the 1000 sub interval, the lower sum, midpoint sum, and then upper sum, they are very very close to each other. So eventually, if this sub interval keeps growing, meaning if this sub interval would be theoretically speaking, if it's infinite, for example 1 million, then this lower sum, midpoint sum, and upper sum, they would give you approximately the same value, and that value would be actually the area under the curve, or area of the region we are looking for. So this is the just the idea to estimate the area under the curve by using the area of the rectangle. So I'm going to do two examples in this section, and then I'm going to talk about this lower sum, midpoint sum, and upper sum to show you exactly how to find this information. So let's look at one example here. Use finite approximation to estimate the area under the graph of f of x equal x squared and above the graph of f of x equals 0. This f of x equals 0 means it's basically y equals 0, which is basically x-axis. So what we're trying to do is we're trying to find out the area of parabola, which is this, but we're going from 0, which is from here, to 8. So let's say 8 is here. We want to find out the area under this curve. So we want to find out this area of this region R. We want to find out this area. Okay, now how do we want to find out? How do we want to approximate this? By doing this different thing. So I'm going to show you one by one. Okay, so the first thing is first thing is a lower sum with the two rectangles of equal width. So this first thing is I want to divide this 0 to 8 interval into two rectangles of equal width, lower sum. So if we try to divide this 0 to 8 into two sub intervals, so that means the midpoint would be 4, because the distance from 0 to 8 is 8 divided by 2 would be 4. So I want to use the lower sum. Lower sum means I want to use the left endpoint in this case. So if we try to draw the rectangle using 0 0, it would be the rectangle of area 0, because height would be 0. The next point would be here, which is 4 comma, the function is x squared, so that would be 16. I want to draw rectangle using this point. So this would be our area, only rectangle. There are actually two rectangles, but one rectangle has area 0 because of the height 0. The first point is 0 0. The second rectangle has area, it's a height which is 16 times width which is 4. So that means the lower sum with the two rectangles of equal width, if you want to estimate that, the lower sum is area of the first rectangle which is at 0 0 would be 0 plus area of this rectangle which is 16 times 4 which is 64. So this is the area using the two rectangles. Okay, so now let me go to the next step, which is a lower sum with the four rectangles. So we are going to use the same approach here, same thing, but we have to divide this interval from 0 to 8 into four different subintervals. So 4 means there will be subinterval of length 2. Okay, and then because it's a lower sum, we are going to draw a rectangle starting with the left endpoint. So left endpoint means starting from 0. If we try to draw a rectangle, that would be a rectangle of area 0. Another endpoint gives us a rectangle of, we need the lower sum, so that is, what is that? I have to erase that thing. So little bit. Okay, so let's come back here. uh, let's go back here, view full screen mode. I have to use this one. From here I have to draw another rectangle. From here I have to draw another rectangle. So we're talking about these rectangles, this one, this one, and this one. As you can see that there are only three rectangles because the fourth one has a height 0. So we have to find out the area of these three rectangles. So as you know, at 2 the height would be 4, at 4 the height would be 16, and because height means it's the value of the function, at 6 the height would be 36. So the area of this three sum, the lower sum, the area of the first one is 0 because there is no height. Area of the second one is, as you can see, that height is 4 and then width is 2, so 4 times 2 is 8. That's the area of the rectangle. And for the third one is, its height is 16 times 2 is 32, and then the third one is 36 times 2 is 72. So the area would be 72 plus 32, which is that right? 72 plus 32 is 104 plus 8 is 112. That's the lower sum using four rectangles, which where the first rectangle has height 0. So that's the answer for the second one. If we try to do the very same thing, using upper sum, what happens? I'm going to show you that using upper sum. So the third one, if we want to do the same thing here using the upper sum, we are using just two rectangle. So that's the middle point is 4. So just compare 1 and third. So look at here. Now to draw rectangles, we're going to use the right endpoint. So what happens is, if you use the right endpoint, which is 416 and 864, right endpoint means we are going to draw a rectangle from here. So this would be our first rectangle. The second rectangle would be from here to here. So as you can see that it's upper sum. So the sum of the rectangle, area of the rectangle would be more than actual area. So that would be area of the first rectangle, which is upper sum using two rectangle. So area of the first rectangle is the width, which is 4 times the height, which is 16, so it's 64, plus the width is 4 times 64 is what is 4 times 64? So 4 times 64, which is let me just use my calculator to make sure that I have the right answer, which is 256. So if we add this two, that would be 320 square unit. That's the area of the upper sum by using two rectangles. I'm going to do the same thing, but this time we're going to use four rectangles. So instead of using the lower sum, which use the left endpoint, we are using the right endpoint. So we are going to use very same interval like 2, 4, 6, and 8. But instead of using the left endpoint to draw rectangles, we are going to use the right endpoint. So this is how the things will be changed, because we are trying to use the upper sum. So we need to find out the area of the first rectangle here, the second one, third one, and then fourth one. So one more time, upper sum. The area of the rectangle means height times width. So width is just 2, height is the value of the function. So this point has the function value 4. So the area would be 8. 4 times 2 is 8. This point has the value of the function 16. 16 times 2 is 32. This point has the value, what is that, 36. 36 times 2 is 72, plus finally the final point is uh, 64 times 8 times 8 is 64. This point is 64 times 2 is what is that, 128. So the answer for this one is 112, which is sum of this three number plus 128. So that means 240, right? 240. So these are the approximation, for area of this region by using lower sum and upper sum, and by using different rectangles. Okay, this is the new problem. As you can see here, let me just make it bigger. Use rectangles, each of whose height is given by the value of the function at the midpoint. So this time we are going to use the midpoint of the rectangle base, the midpoint rule. Estimate the area and the graph of the function using the first two and then four rectangles. So I'm going to use two rectangles and then four rectangles using the midpoints. Okay, so in this case, as you can see, the graph is, let's start with the two rectangles. The function is a reciprocal function, which is 5 over x. So this is the graph of the function look like 5 over x, and we're going from x equal to 1 to x equal to 17. And the first one, we're going to use two rectangles, so that means we're going to divide this from 1 to 17. We're going to divide this into two pieces. So 1 to 17, the difference is 16. So the middle point would be 9, x equal to 9. So we are going to use two rectangles, and to draw the rectangles this time, make sure that this time we're not using the left endpoint or the right endpoint. We're going to use the midpoint of this subinterval. So what is the midpoint of number between 1 to 9? It's the sum of the number divided by 2, which is 9 plus 1 is 10, divided by 2 is 5. So this is the midpoint. So to draw rectangles, we are going to use this height, which is at 5, because the value of the function is 5 over x, which is basically 1. So we are going to draw a rectangle using this height of the midpoint. Similarly, for the next one, the midpoint of 9 plus 17, 9 and 17 is 13. So 13 is the midpoint. So to draw another rectangle, we're going to use this height. When x is 13, the y value is 5 over 13. So if we draw a rectangle through this, we have to use area of these two rectangles. So the area, approximate value, or the area of the rectangle, using rectangle each of whose height is given by the midpoint. So midpoint approximation or midpoint sum is equal to area of the first rectangle, which is the width, which is 9 minus 1 is 8, times the height is 1, so this is 8, plus the area of the second rectangle. Again, the width is 17 minus 9, which is 8, and height is 5 over 13, so it's 8 times 5 over 13. Okay, so basically it's 8 plus 8 times 5 is 40 over 13. So we can just use our calculator to find out 40 over 13 plus 8. So I'm going to use my calculator here. If I divide 40 by 13 and then add 8 to that, it will give me 11.0769, and then other number. So this is the midpoint sum for these two rectangles. So one time by using two rectangles, and second we are going to use the very same function, but starting from 1 to 17, instead of using two rectangles we have to use now four rectangles. So we are dividing this interval from 1 to 17 into four equal sub intervals. So the difference between them is 17 minus 1 is 16. So four equal pieces means four, the width would be 4. So the next point would be 5, next point would be 9, next point would be 13, and then we are going to draw rectangle using the midpoint of each of these subinterval. So midpoint of each of these subinterval. Okay, like here. So I have to erase this. Let me this one. Okay, let me use a different color here. So okay, so here the midpoint of each of them, the midpoint of 1 and 5 is what is that, 3. So this is the point I have to use to draw rectangles. So at 3 the value would be 5 over 3. The second midpoint would be a midpoint between 5 and 9, which is 7. So I need to draw rectangles using this point, which is at 7. The value would be 5 over 7. The third midpoint is between 9 and 17, which is what is that, 13. So here I need to draw rectangle at 13, which is 13 comma 5 over 13. And finally here in between, what is that? Okay, so this is okay what I did. So the first one is 1, 5, 9. This is 13. So in between 9 and 13 that would be 11. So it should be, instead of 13 it should be 11. Okay, and then third one would be 15. So 15 comma 1 over 3. Okay, so this would be 11. So these are the midpoints and then height of the corresponding rectangles. So now midpoint sum by using these four rectangle would be, we know the width is 4 for each of them and height is the y value at the midpoint. So the first one, as you can see, that is 5 over 3 times width is 4. The second one is 5 over 7 times 4. The third one is 5 over 11 times 4. Fourth one is 1 over 3 times 4. So as you can see that the 4 is common here, so I'm going to just add 5 over 3, 5 over 7, 5 over 11, and 1 over 3, and times it by 4. So I'm going to use my calculator here. So the value would be, let me just use my calculator, 5 over 3 plus 5 over 7 plus, and 5 over 11 plus 1 over 3 plus, and times it by 4. Altogether it's approximately 12.675. Okay, so that is the approximation. Just use your calculator and find out the area of this rectangle using which is drawn by using the midpoint of this subinterval.